Imagine wrapping the entire Earth in a ring of copper. Not cable, not wire rope, but nearly 500 million tiny copper needles, each one thinner than a human hair, each one orbiting silently 2,300 miles above every war, every crisis, every nuclear standoff. That was the plan. And an engineer named Walter Morrow actually did it. This is the story of Project Westford, one of the strangest ideas the Cold War ever produced, why it worked, why it didn't matter, and why some of those needles are still up there today. It's 1958. The United States and the Soviet Union are locked in the most dangerous standoff in human history. Both sides have nuclear bombs, both sides have missiles. The only thing keeping the world from blowing up is this: neither side wants to fire first because they know the other side will fire back. But that plan only works if your military can actually talk to itself. And here's the scary part: the Americans weren't sure it could. The U.S. military had forces all over the world, soldiers in Germany, ships in both oceans, radar stations in the Arctic, bunkers buried under mountains in Colorado. All of them needed to receive orders from Washington the moment anything went wrong. They had two ways to communicate. First, underwater cables stretched across the ocean floor, basically the internet cables of their day. Second, radio signals bounced off the upper atmosphere, a layer of electrically charged air about 30 to 600 miles up, called the ionosphere. Both had a giant problem. Those underwater cables, a Soviet submarine could cut them. In the opening hours of a war, the U.S. could suddenly go deaf. And the ionosphere? Nuclear explosions in the upper atmosphere could knock it out completely. They knew this because they'd already tested it. In the summer of 1958, the U.S. military detonated a nuclear warhead high above the Pacific Ocean, not to destroy anything on the ground, but to see what it did to radio signals. The answer was alarming. Radio communication across large parts of the Pacific blacked out for up to 9 hours. The explosion had essentially switched off the sky. Pentagon officials grew so worried during the blackout that when contact with Johnston Island was finally restored, the first message sent was simply, "Are you still there?" The lesson was brutal. If war came, the very tools the military needed to survive it could be wiped out in minutes. They needed a backup, something that couldn't be cut, something that couldn't be jammed, something that a nuclear bomb couldn't touch. They needed something that didn't exist yet. Walter Morrow had spent 7 years obsessing over how radio signals bounce around the upper atmosphere. He joined the MIT Lincoln Laboratory in 1951 at age 23, right after finishing his master's degree in electrical engineering. He was the kind of engineer who mapped out every consequence before he ever picked up a pencil. His colleagues called him methodical, quiet, precise. As a kid, he'd built what he called hopeful perpetual motion machines, devices he knew were physically impossible, but building them taught him exactly where beautiful ideas collide with the real world. That gap would define his life's work. And here's something almost nobody knows about Walter Morrow. The year after he joined Lincoln Laboratory, 1952, he designed what was probably the world's first transistor flip-flop. If you've never heard of a transistor flip-flop, here's why it matters. It's one of the fundamental building blocks of every digital computer ever made. Every phone, every laptop, every server running the internet today traces part of its ancestry back to that kind of circuit. Morrow helped lay the groundwork for the digital age at age 24, and then went right back to staring at the ionosphere. Hold that thought, because the digital revolution he helped start is the same one that would eventually make his greatest achievement completely irrelevant. By October 1958,
Morrow had an idea so enormous it almost sounds like a joke. If the natural ionosphere, the layer of atmosphere that reflected radio waves, could be destroyed by a nuclear bomb, why not build an artificial one that a bomb couldn't touch? His plan: launch a ring of copper needles into orbit around the Earth. Not a few needles, not a few thousand, 480 million individual copper needles, each cut to exactly the right length, each thinner than a strand of your hair. Together, they would form a belt around the planet, sitting quietly in space 2,300 miles up. Here's the physics as simply as possible. When you cut a piece of copper wire to exactly half the length of a radio wave, it becomes an antenna. It absorbs the radio signal and bounces it out in all directions. A thick enough cloud of those tiny antennas surrounding the entire Earth would bounce microwave radio signals from one side of the planet to the other. No electronics, no power source, no satellite to shoot down, just copper. He called it Project Needles. The numbers were staggering. 500 million pieces of copper, each about the size of a sewing needle, each weighing almost nothing. Together, the entire belt would weigh less than one person, somewhere between 40 and 60 pounds total. And it would orbit the Earth silently, invisibly, useful as a global radio reflector for years, before solar pressure gradually pushed each needle back into the atmosphere, where it would burn up harmlessly.
The military loved it. Within months, they funded the project, assigned a team, and gave it a new name, Project West Ford, named for a small town in Massachusetts where the observatory that would track the needles was located. But the rest of the world was not impressed. When news of the project reached the broader scientific community, the reaction was fierce. Astronomers, both radio astronomers who study invisible energy from space and optical astronomers who study visible light, were furious. Their concern: 500 million copper antennas floating in orbit could interfere with their ability to see the universe. The International Astronomical Union formally opposed the project. Britain's most famous radio astronomer, Sir Bernard Lovell, who ran the world's largest steerable radio telescope, wrote letters of protest. He wasn't just worried about the needles themselves, he was worried about what the project represented. His point: the United States was treating near-Earth space as if it owned it. They were planning to fill a part of the sky that belonged to everyone without asking anyone. Fred Hoyle, a famous British scientist, called it a major intellectual crime. That phrase showed up in newspapers around the world. The Soviet newspaper Pravda ran the headline, "USA Dirty Space." This was propaganda. The Soviets had their own secret military space programs, but the headline landed because it voiced what many people were thinking. The controversy went all the way to the United Nations. The U.S. ambassador, Adlai Stevenson, had to stand before the General Assembly and explain why America had decided to place 480 million pieces of copper in orbit. His answer: the needles would naturally fall back to Earth on their own within a few years. The project was important for national security, and the U.S. had published its plans openly. These were all true statements, but they missed the point the world was actually making, which was, who gave you the right to do this in the first place? Inside Lincoln Laboratory, the protests were treated mostly as a PR problem to manage. The engineers had done the math. The interference would be minimal, the needles would deorbit, move on. But the engineers were thinking about physics. The world was asking a different question. Who owns space? Building the needles was its own kind of insane engineering challenge.
Each needle had to be cut to within a fraction of a millimeter of exactly the right length. Get it even a millimeter wrong, and it wouldn't work as an antenna. The team had to produce nearly 500 million of them this way. The needles were so thin and so light that air currents in the lab could move them. Static electricity would fuse hundreds of them together into tiny, tangled knots. They looked less like individual wires and more like tiny glints of light. The release mechanism was the trickiest part. You couldn't just dump 500 million needles into space all at once. You'd get one dense local cloud instead of a belt stretching around the Earth. The solution? Embed the needles in naphthalene. You might know naphthalene better as the stuff in old-school mothballs. In the vacuum of space, naphthalene skips its liquid phase entirely and goes straight from solid to gas, a process called sublimation. As it evaporated, it was supposed to release the needles slowly and evenly across the orbital arc. It worked perfectly in every test on the ground. On October 21, 1961, the first attempt launched from California aboard an Atlas rocket. But here's a detail the history books leave out. The needles didn't get their own rocket. They were strapped to the side of a classified missile detection satellite called Midas IV, part of a top-secret early warning program designed to detect Soviet missile launches from space. The needle experiment literally hitchhiked into orbit on top of one of America's most sensitive Cold War weapons programs. Even the launch was a secret inside a secret. It reached the right orbit. Ground controllers sent the command to activate the dispersion system. Nothing happened as planned. In actual space, the naphthalene didn't evaporate evenly the way it had in lab tests. Instead of releasing needles gradually, the mechanism produced 4 or 5 dense, tangled masses of copper wire, each one estimated to contain hundreds of thousands of needles fused together, which then just floated there, doing nothing, reflecting nothing. 4 masses, each one roughly the size of a tennis ball or larger, packed with what may have been millions of needles that never separated. After years of engineering work, millions of dollars, and a diplomatic fight at the United Nations, 4 useless balls of copper wire in orbit. The team spent 2 years figuring out what went wrong. They redesigned the dispenser, added a spinning mechanism to help separate individual needles as the naphthalene evaporated, and ran more extensive ground tests. Meanwhile, those 4 tangled masses from the failed 1961 launch were still up there, orbiting. They are still up there today. On May 9, 1963, the second attempt launched. This time, the dispenser worked. The needles spread. Instruments picked up the signature of a cloud of copper forming in orbit. And then, the test that mattered. Engineers in California pointed a large dish antenna at the sky, right where the needle belt was passing overhead, and transmitted a signal at 8 gigahertz, the exact frequency the needles had been cut to resonate with. The signal traveled 2,200 miles upward, hit the copper cloud, scattered in multiple directions, and a portion of it continued east. In Massachusetts, more than 2,800 miles away, a receiving antenna picked it up. 2 stations, separated by the width of the United States, had just communicated through a cloud of copper needles orbiting the Earth. Think about what that moment actually was. Someone in California spoke words into a microphone. Those words traveled as a radio signal straight up into space, hit a cloud of 500 million copper needles 2,200 miles above the Earth, bounced off them, and traveled back down to a dish antenna in Massachusetts, all in a fraction of a second. We don't have a recorded transcript of exactly what was said in that first successful exchange, but the engineers described it clearly. A recognizable, real-time human voice received cleanly on the other side of the country, bounced off copper in orbit. The space age had its own Mr. Watson come here moment, and almost nobody knows it happened. It worked. The data rate was modest, about 20 kilobits per second, enough for voice calls and text transmissions, but the physics Morrow had proposed in 1958 was proven. The engineering had succeeded. Walter Morrow was 35 years old. There was just one problem. While the Lincoln Laboratory team was redesigning the dispenser after the 1961 failure, AT&T launched a satellite called Telstar 1. Telstar didn't passively bounce signals the way the copper needles did. It caught incoming radio signals, amplified them electronically, and retransmitted them stronger. It was essentially a radio repeater in space. One day after launch, on July 11, 1962, Telstar relayed its first television pictures. 2 weeks later, it broadcast the first live transatlantic television signal, the Statue of Liberty, the Eiffel Tower, and a message from President Kennedy, watched by millions. With far simpler ground equipment than West Ford required, Telstar could carry multiple simultaneous phone calls and TV broadcasts at once. West Ford's 20 kilobits per second, achieved with giant 60-foot dish antennas, couldn't compete. And Telstar wasn't even the first sign the writing was on the wall. A year before West Ford's failed 1961 launch, NASA had quietly put up a satellite called Echo 1, a 100-foot aluminized balloon, basically a giant silver beach ball floating in orbit. It was so bright that millions of ordinary people could see it moving across the night sky with their naked eyes. No telescope needed, just look up. Echo 1 worked on the same passive reflection principle as the West Ford needles, bounce the signal off something in orbit. But it was completely public, completely peaceful, and anyone on Earth could watch it pass overhead. While Morrow's team was secretly launching needles on top of a classified missile satellite, NASA was bouncing phone calls off a balloon that school children were tracking from their backyards. The fundamental physics of the problem had changed. A passive reflector, no matter how many copper needles it contained, could only bounce back a small fraction of the energy hitting it. An active satellite could amplify. And as transistors kept getting smaller and cheaper, active satellites would only get better. Passive reflectors would stay exactly the same. Military planners concluded by the summer of 1963 there was no point continuing. West Ford was canceled before the end of the year. Not because it failed, because it succeeded and proved itself immediately unnecessary. Lincoln Laboratory's own internal review admitted the system had worked perfectly and ultimately changed nothing. It worked, and it didn't matter.
Here's where the story gets strange. Most of the individual copper needles from 1963 deployment did exactly what Morrow predicted. Solar pressure gradually pushed them back toward Earth, and they burned up in the atmosphere within 3 to 5 years. But those tangled masses, the sections where the naphthalene had failed to vaporize completely, leaving dense knots of hundreds of thousands of needles packed together instead of dispersing individually, those were a different story. A tangled mass has much less surface area relative to its weight than a single needle. Think of it this way. One loose needle catches the wind easily. A tight ball of needles barely feels it. Solar pressure barely nudges them. They've been slowly losing altitude for over 60 years, dragged down gradually by the faint wisps of atmosphere that extend even to that altitude. From the failed 1961 launch, 4 tangled masses, each potentially holding millions of needles. From the 1963 deployment, only 15 to 40% of the needles actually dispersed directly. The rest stayed locked in dense knots of hundreds of thousands of needles instead of dispersing individually. By the 1990s, space agencies were tracking 8 to 12 distinct West Ford debris objects larger than 10 centimeters. By the mid-2000s, that number had grown to 44 trackable objects. As of 2023, still 44. That's just the ones big enough for radar to see. Here's what that number doesn't tell you.
Scientists estimate there may be tens of thousands of smaller needle clusters, too tiny to track individually, invisible to radar, unaccounted for, silently orbiting at 2,200 miles up. They're not going to hit the ground anytime soon. They're not a direct threat to people on Earth, but they do pose a small but real collision risk to the satellites we now depend on for GPS, weather forecasting, communications, and the Internet. And here's the deep irony. In 1977, Walter Morrow was appointed director of MIT Lincoln Laboratory, the same institution that had built the needles. Under his leadership, beginning in 1989, the laboratory began operating powerful radar systems to track orbital debris. The Millstone Hill Observatory in Massachusetts, the very facility that received the first West Ford transmission in 1963, became one of the primary tools for monitoring space junk. The lab that put the needles up there now watches them. The man who designed them spent 21 years as director of the institution tracking them. Walter Morrow died in February 2017. 4 of those tangled masses from the 1961 failure, each one a dense knot of what may be millions of his needles, were still in orbit the day he died.
So, what's the point of this story? Project West Ford was not a failure of bad intentions. Walter Morrow was trying to solve a real problem, a genuinely terrifying one, with an approach that was creative, mathematically sound, and ultimately successful on its own terms. But the project did something more important than solve its original problem. It started a fight. The international protests against West Ford, the astronomers' letters, Fred Hoyle's outrage, Pravda's headline, and Adlai Stevenson's awkward defense at the United Nations established something new, the idea that near-Earth space was a shared environment, that no single nation could just dump things into orbit without considering the effect on everyone else. That principle eventually shaped the Outer Space Treaty of 1967, which requires nations to act with due regard to the corresponding interests of all other states when using space. Today, SpaceX's Starlink constellation has launched more than 7,000 satellites, with plans for tens of thousands more. Astronomers are protesting, many in the same language about the same concerns, that a private company is filling the sky without adequate international consultation. The fight that started with 480 million copper needles in 1961 is still going. The 44 tracked objects are still orbiting, and behind them, tens of thousands of smaller needle clusters too tiny to see. Small and silent, each one a reminder of the gap between what an idea looks like on paper and what it leaves behind in the real world. If you found this story as mind-bending as I did, hit subscribe. We cover the forgotten stories that quietly shaped the modern world.